Okay, hello again. Hello after the short break. So please welcome Joydeep and his presentation are the free-based DSLs for distributed compute engines. The floor is yours.
Thank you. So, hi everybody. I'm audible? Okay. So, thank you for joining me for this talk. A little bit of introduction about me. My name is Joydeep, as you already know, and I work as the head of data sciences at Zeotap. Zeotap specializes in providing CDP, customer data platform, and global data for in the European region. So you can go check out our website and see more about what we do. This project that we have created is primarily for one of our global data platforms. So let's start. So the topic is free-based DSLs for distributed compute engine. As you've already guessed, we are going to talk a lot about free monads and the free DSLs, right? Okay. So what was the motivation? So at Zeotap, we have a lot of heterogeneous pipelines. When I say heterogeneity, I talk about different kinds of execution engines, Spark, Dataflow, which is primarily on Apache Beam, BigQuery, that kind of heterogeneity. And then there was a lot of SQL-based transformations, SQL-based processing, and then there was custom business logic, custom processing logic, which could not be modeled using a SQL. And then the code was, again, with Beam, it's in Java, and with the Spark, it's in Scala. So let's now focus on the problem statement. What were we facing? What was the problem that we were trying to solve? So a lot of times, if you guys have worked with Spark or Pandas, as a matter of fact, you'll find that there's a lot of coupling of the business logic with the runtime engine, right? You write a lot of the business logic with using your Spark dialect. Once you do that, you cannot pick out that logic, although that is reusable somewhere else. You cannot pick out that logic and use it somewhere else, right? So generally, our product teams would talk. Let me give you an example. Our product teams would talk in terms of some business language, right? So if data is coming in, product team might want to do some data quality checks. They might want to say that particularly a column is not null, or particular values should be present in these columns. Now, it doesn't matter whether you're processing it in Spark or Beam or BigQuery. It doesn't matter. The business language remains the same. The product team's communication remains the same, right? So that was one of our problems, that at multiple places, similar code was getting replicated, and again in different runtime engines, right? So again, what I have pointed out here, no code and functionality reuse, right? So some logic written in Spark, a very similar logic again written in Beam. At the same time, because there was no unified platform, there was no way of unifying all this logic at one place. Everybody would just go about writing their own custom code in Spark using the data frames and those kind of APIs, and it would be a mess. So our first thought was to arrange everything at one place, was to put everything in perspective, and then again reuse the same business language for different runtime engines. So, okay, what were our design considerations? So if you see here, I have put something at the top, which is a domain-specific language. So basically, as I was talking about, the product teams talking to us in a certain language, right, which is not dependent on the runtime engine or the data processing engine that you're using, right? They would generally talk in a standard business language. So we needed some kind of a standardized DSL, right? And again, we needed some way of segregating the platform and the domain. The domain is business, and the platform is what I'm talking about, the runtime engine. So we wanted that segregation as well. And once we have done that segregation, what we also figured out is, once we have written this standardized business language, there were different kinds of way of composing them. One way of composing them is what is a sequential control flow, right? Where the output of the previous operation would be an input to the next operation, right? And then there were also a lot of them who were independent. I need to check say suppose I'll take an example of a demographic column, gender. I need to check whether the column is non-null, as well as I need to check whether it contains male and female or not, right? Those two computations are independent, and we can do them parallelly. There is no dependency on the previous computation, right? So we needed a overall, system to, tackle these complexities and in a very functional way. So as a result, we came up with these 3 projects. 2 of them is open source. You can go check out the code. And the first one is, as you can see, we named it ZeoFlow. It's a general model of computation. Any pipeline today, if you go, there are some basic steps that are involved, right? You read the data, you do all kinds of transformations on top of it, you do some data quality checks, and you write the data. That's pretty much it, right? And then there can be different kinds of nuances there, but that's pretty much the high-level steps. And then we had the data quality, which we figured is in itself a huge project. There are different kinds of checks that you would like to do on data quality, right? So giving it a separate project called data expectation is what we did as a solution. And then finally, we had this project, Data IO, which primarily deals with reading data from blob storage, writing data, and then we had a lot of Zeotap specific features, like say suppose whenever you read a data set from S3 or GCS, you want to append some columns by default. These are our standard columns, right? So this is Zeotap specific business language. We wanted this out of the box. Somebody should be able to just compose that domain or business language and they should get it out of the box, right? So we needed some sort of standardization there as well. So having said this, what we are going to really see in today's talk is how the free-based DSLs, the free monads and the free applicatives actually helped us achieve this. And I hope we get to learn about free in the process. Okay, so I've been talking about DSL a lot. So quickly, let me get it out of the way. What is a DSL? We all know it's a business language. As you can see, a little bit technically, if I put it, it has an inherent meaning pertaining to business, right? It talks about the what, right? It does not talk about, forgets about the how, right? How you're going to process this data, how you're going to work with this data, using Spark, using Beam, using BigQuery, it doesn't matter. It talks about what is there in the data and what's the functionality that you want to achieve, right? You want to load the source, you want to run the transformations. I can take this and I can make it a high-level business language, right? At the same time, I can do data quality checks as a high-level business language, right? So it is not bothered with implementation. Okay, so we figured that we needed a few characteristics. So while we were evaluating different kinds of data structures or different kind of solutions, we figured we needed these characteristics, right? So as you can see, the business language is very akin to an AST, an abstract syntax tree. We needed some way of writing our own AST, right? Writing our own language. And it definitely probably need to have a monadic behavior, need to work like a monad. But we'll see it also can work like an applicative. And again, the segregation of the runtime engine needs to be there, right? We need to swap in and swap out, say, a Beam or a BigQuery at runtime, right? So we needed plug-and-play interpreters, right? So the DSL should be independent of that. The DSL code should not get interlinked to these interpreters. So I think the easier choice was the free DSL. So before going into the free-based DSLs, I want to talk about reification. So what is reification, right? So it's simply put, it is this, something which was abstract in your code, make it concrete. So you have some concept which is implicit in the code, you turn it into data, which can then be manipulated by the program, right? You can take an example of this in the option monad, right? Where you have the concept of partiality. Or in Java, if you see, we would handle this nulls, right? If something is null, then do this, then do that. What you inherently implicitly imply is you want to do some sort of, you want to say that your program partially responds to some questions and doesn't respond to some of them, right? Now we are making it a first-class citizen. And really, reifying is at the essence of functional programming because you take anything that was implicit, any concept that was implicit, and now you turn it into data and play around with it, right? So let me give some examples here. I'll just quickly go to the, yeah. So if you see overall functional programming itself, in conventional OOPS, right? Functions were not data, but in functional programming, you can pass around functions, right? As I gave an example for the option monad, right? The concept of partiality is getting, reified using the option monad. Otherwise, you would have to do these null checks, which would be implicit in your code, which you would do anyways, but there is no standard construct for it. But here, you have a standard construct, right? And it is everywhere, actually. If you see Kleisli, that is reification of the concept of effectful composition. Trampoline, if you've used the cats, you'll see it's reification of stack safety, right? And if you see DSL itself, what we're trying to build, what we're trying to do really is, it's a very famous paradigm in functional programming that you take some concept, you turn it into your abstract data types, and then later you try to interpret them, right? And you try to execute them later. You first do a definition of it, and you later execute them, right? So that is, again, reification, okay? So to give you an example, so that I've been talking about reification a lot. So if you see, earlier you would write a method like this, load sources. I'm just giving an example from Zeoflow itself. You talk about these load sources, which would take in a list of string, which is probably your source paths from where to pick from S3 or GCS, and would return a data frame. And then you would have a write to sync, where you take the sync path where to write the data to, and it would not return anything. So what we did was we kind of reified this, right? And we reified the concept of load sources. If you see, there is a uncanny similarity between the both, right? It's still taking the source paths as a list of sources, and it is extending it with flow DSL, right? So I'll come to this. What is flow DSL? I'll come to this, but I just wanted to show you an example of this, okay? So same goes for the write to sync. We have created an ADT out of it, and now we're extending the flow DSL. So what are we trying to do? So I have already told these steps earlier. So if you see, this is what the Zeoflow DSL is doing, okay? If I have to break down into atomic steps, if I have to break down my computation, the work that I do with Zeoflow into atomic steps, what I do is I load the source, I load the user-defined functions, and this is, I think, available everywhere, right? You have user-defined functions everywhere. And run the transformations, assert data quality, write to sync, send alerts. This is pretty much more or less. There can be more to this vocabulary, there can be less to this algebra, but this is pretty much it. And this is how we define it. Okay, so you can just gloss over this lot of code here, but what you can focus on are the parts which I have highlighted. If you see, there is a float DSL, which is a sealed trait. You cannot, and the float DSL is based on a generic type, float DSL of A, right? And we will show that later why we needed an A. But the point is, if you see load sources extends the flow DSL, load user-defined functions extends flow DSL, all of them extend flow DSL, and this you would do anyways in your program, right? We took it and we reified it and made it, algebraic data types, right? Okay, so I've spoken about this business language DSL AST that I have created. What do we intend to do? Before moving ahead, I would just like to detail the steps that we intend to do, right? First, we have created the DSL already. So next, we need to lift it into a free. I'm going to show that how. Then, using that, we're going to construct some sort of program, right? We're going to mix and match. We're going to, maybe sometimes I just load the sources, run the transformations, and write to sync. And maybe sometimes I just load the sources, load the user-defined. So there are multiple variants possible, right? So we'll get to that. So we provide interpreter. Next, we provide an interpreter for this DSL. This is where the runtime engine comes into picture. And finally, we invoke the program using this structure. So this is program represents your business flow, and then you kind of fold it over, and you pass the interpreter into it. So we'll see example for this. But this is the overall step. Okay, before moving forward, I would like to, kind of set this base intuition of what to think about free. We have been talking about free a lot, and free has helped us and things like that. What is this free? So if you see, what we have defined here, if you remember from the previous one, we had defined this seal trait, and there was no mention of free here. This is my business language. This is my AST. I've gone here, and I've created a free of flow DSL, comma A. Okay? This is where it gets interesting. How do you think about this flow DSL? You can think about free of S, comma A, where free is the program which takes your S, which is flow DSL, which takes your language, your AST as an input, and computes the value A. You can just think of it this way. It is the program which takes your language as an input. Somehow it takes your language, the things that you have defined as an input, and calculates A. Okay? Two other points I want to point out here about free to set some notion. One is it provides a monad. It provides monad on your AST or DSL. So what does this mean? This line. So what I have been talking about, why I have been talking about this AST? Because eventually I'm going to do some work with it, right? When you write a SQL, there are steps in that SQL. Similarly, when you write base atomic steps, right? So the load sources, the run transformations, the write to sync, all of these are steps. I would have to be able to sequence them. I would have to be able to compose them, right? How do you compose them? You can only sequence them if you have a monad available, right? But we've just written the DSL. We don't have a monad available on top of it. Definitely, now that I have put it into a free, probably free has that monad available. Probably free has a flat map somewhere which will help me in sequencing it, right? That is one. And second is, another point which I again wanted to make is, till now if you see, we haven't spoken about any interpreter, how to run it. We're just talking about the business language, right? It completely separates your AST, your DSL from the interpreter. We're not talking about, spoke about loading the sources and running the transformations. We've not spoken about where I would load these sources, using what technology, what runtime engine. No, we haven't spoken about that, right? So just by defining this, we should be able to work with it, okay? So let's see how we can work with it. This is provided by CATS, Scala CATS library. You lift, so if you remember from the previous slides, load sources and write to syncs was the ADT for my flow DSL. So you just lift it into a free like this. One thing that you would want to note here is the return type of these lift F is a free flow DSL of A. Okay, because if I don't provide a return type explicitly, the return type would be actually a load sources, because load sources itself is an abstract data type, right? It extends free flow DSL, right? Load sources extends free flow DSL, so it's itself an abstract data type. So if I do not provide a free flow DSL as a return type, it would take load sources as the return type. What's the problem with that? Because the problem is you'll not be able to compose, you'll not be able to use it in a for comprehension. All of them needs to be of the same monadic type, right? Free flow DSL is the hierarchical monad here. So everybody needs to be of type free flow DSL for me to be able to use it in a for comprehension. So these are some examples. So once I've defined this, what I did was I defined my AST, I defined a free based on that. I lifted all my atomic units into the free. And now what I'm going to try to do is start writing different kinds of business flows. Okay, so I've just put some variants here, if you see. Variant 1 is maybe load the source, run the transformations, write to sync. Variant 2 is load the source, run the transformations, don't write to sync, assert data quality on top of it. Variant 4 can be load the source, run the transformations, assert data quality. If quality passes, write to sync, else send alerts. Okay, so these are the different kinds of program structures that you can have, or business language that you can have, right? So if you see this is just some code example, again, you can focus on the highlighted parts, okay? So this is what I have been talking about. Because load sources, load user-defined functions, run transformations, all of them had a return type of free flow DSL, right? Now I'm able to compose them, Right? Otherwise, I would not have been able to compose them. Okay, and what I've tried to show here is two different types of flow. And now probably you would see the use of that free flow DSL of A. I did not bind it to any return type. So here, this program, this one here returns a unit, while this one here returns some expectation result. And that's the, that's the good part about not binding a free flow DSL with any return type. If you remember, we had the free flow DSL as free flow DSL of A, right? So now I can write not just write different kinds of compositions, I can return different types from there as well. So this is what it means, this unit and expectation result. Okay. So yeah, I've created my programs now, I've created my business flow, right? But as I've already mentioned, till now, I've not spoken about any implementation, whether I have to run it on Spark, whether I have to run it on BigQuery, I don't know. I've just created a business language out of it, pretty much a model of computation, right? Next, this is where, so now I'll try to provide some interpreters, okay? So if you see here, what we are using here is something called a function K, where it kind of maps your flow DSL to an IDE. But IDE is another monad. You can use any monad here. I've just shown a very simple example. Probably we'll see other examples later in the slide. So what we are doing is, at a high level, if you think, whenever you encounter a load sources, you do something here. Here I have, here I've just done a println, right? But this itself, this ID can be another monad, and we do some sort of monadic stuff here. We do some sort of operation here. And this ID can be, this is where your implementation comes in. This can be some kind of a Spark data frame related monad, right? And then you do all sort of Spark transformations here, right? These load sources, you do all sort of Spark dataset loading here. If it's BigQuery or say Beam, you write your Java code here as well, right? Where you load your, Beam datasets, P collections, right? So this is where the beauty of it lies. You take one DSL and you target it to multiple runtime engines, multiple interpreters, right? And that's what probably is the takeaway, is you can take this flow DSL, which is completely your AST, lift it into a free, provide these interpreters where now you can target it to different, for me it was runtime engine, but for you, it can be something else completely, right? You're doing one implementation for the web, one for the mobile, right? So this is the interpreter, and then, okay, this function K we're going to see later. It's called a natural transformation, which kind of, if you see what it does at a high level, very succinctly is keeping the A constant, it helps you to transform F to G. Okay, it's kind of, somehow it's helping you to take this F and convert it into a G. Okay, how we'll see later. Okay, and finally the invocation, because I just want to get over with this part first so that you see a complete flow. So now how do you invoke this is basically, if you remember, we had created these programs earlier, right? This one here, end-to-end flow, okay? So what I'm doing is, I'm just calling this end-to-end flow with a fold map, and I've written the interpreter. I'm just passing that interpreter. This interpreter might as well be a Spark interpreter, or a Beam interpreter, or a BigQuery interpreter, okay? The general structure is this. You kind of fold over this program. This is the program, this is your business flow. You call a fold map on top of it and pass the interpreter from outside, okay? So this is the general pattern. Okay, so now I think we ought to discuss a bit about the free data structure as well, because we've spoken a lot about free, how we can pass the interpreters, what sort of things we can do with it. So if you see here, what I really want to convey is, you had not written a monad, you rewrote an AST, which was completely your business language. Somehow, free is able to convert it into a monad, okay? Free is able to provide those monadic functionalities. So obviously there's going to be a flat map somewhere down the line, but free is able to do that for you, right? But what that also means is there must be, so free should be, kind of taking all these atomic units And it must have some kind of data structure which stores all these atomic units, okay, which kind of puts all of my computations within its data structure, and then we are able to traverse it later and interpret it later. First, we are defining our DSL, and what free internally would do it would store all of these data structures. It should be doing that. I don't know. We'll see. And the point being, if it does, then just like my DSL had an algebra to it, free would also have an algebra to it, right? But question is, what kind of algebra? What kind of algebra are we looking at free here? So intuitively, if you think you had this DSL, you kind of got this structure, data structure from somewhere free, you lifted it, and suddenly you have these monadic capabilities. So free actually is reifying the concept of a monad, right? So what does reifying a monad means? Something which is implicit, make it data. So what is implicit in a monad? Point and flat map, right? And now free is trying to reify that as well. So that's why I have put it here. If you see, a monad where I have put this point and flat map, if you see the ADTs of free itself are very akin to monads methods, right? PR, if you see here, you have an A and you get a F of A, and you have an A here and you get a F of A, right? And same goes for flat map. Also, it's not the same, but if you see, at least this part is similar, okay? So definitely, free has this data structure, which kind of reifies the concept of a monad. And if you want a more explicit view, this is how it stores your data. All this suspend comes from here, and in between lies your steps, okay? Your DSL, run sources, or load the sources, run the transformations, write to sync, all lies in between these data structures, and the terminal point is a pure. So what you do is you just kind of traverse this one by one until you hit a pure, okay? And that's what really free is providing you, reifying the concept of a monad. So let's, now we've already spoken about free and we know it's a monad. So let's try to see what would be the implementation of this monad, okay? What would be the implementation of free itself? So obviously we're gonna, it has to abide by the interface of a monad. So it has to have a point and a flat map. You can call it pure or a flat map. First one is pretty easy. If you see here, point here, right, A, you just wrap it in a pure because the return type has to be a free, so you wrap it in a pure, right? That's it. Flat map would be a bit more involved. So let's tackle the pure part first, which again is basically you pull out the A from here and pass it into the F. Pretty simple, okay? Let's go to suspend, okay? And one thing that we say in functional programming, if you don't know what to do, just follow the types. See what fits where. We're just going to kind of reverse engineer, see what fits where, and try to come up with the solution over here. Okay, so obviously I have to return a free. So what can I return? I can return a suspend over here. So definitely what I'm going to return from here would be a suspend, okay? Now let's see what we can do. Okay, so if I had a free, I would be able to, so what are the operations available? I have a F here. Somehow I have to use the F, and I have to use a free. If I had a free, I would be able to flat map over it. Okay, but I might be running here. So if you see, where does this free come from? So if you remember, this was your data structure, right? F of free of F of A, right? So this is where I get the free from, free, and I'm able to call a flat map on top of it. But the problem is, how do I get this free? It is within this F, right? And F is something defined by you, right? But more than that, say suppose somehow I did it, how would I do it? The ubiquitous function that we use here is the map operation, right? To pull something out, to transform something, to map over something, right? So probably if I would have got a map on S, right? I would be able to, pull out the free and work with the free and pass it in a flat map, probably. But I don't have a map on S. This is a data structure, or this is an ADT defined by you. This DSL has been defined by you. I have not said that it is a functor. You cannot have a map on top of it. So this is where the only requirement that comes for free, it is there has to be an implicit functor available on your DSL. Okay, if this implicit functor is available on your DSL, then I can call a map on top of S, right? This is the only requirement for free. The DSL that you write has to have an implicit functor available in the scope, okay? How do we do that? It's very simple. CATS provides it for us, okay? CATS is the library that provides this for us. If you see, it has something called Koyoneda. It's a lemma. You can read more on it. But the idea is it can take any higher kinded type constructor. This is your higher kinded type constructor, which you have written. Okay, it can take any higher kinded type constructor and convert it into a functor. And just like that, you have a functor available on which you can map. Okay, so this is where Koyoneda or the CATS library comes into picture, and why we use the free from CATS. Probably Scala Z also provides the same. You can use either. Case in point, so in principle, now if I talk in principle, what free does is it takes a functor and it adds the pointed part and the monadic behavior to it. That's what we showed, right? The pure and the suspend, right? That's what it does, really. Okay, let's move on. Okay, so just, we've gone through a lot of theory. Just now putting all that theory in a bit of, technical term. We've spoken in very business language kind of view. Let's put it in some technical Scala language. So what we do is we first define a higher kinded type, which is this. This is your higher kinded type. We lift your higher kinded type to a free, right? That's what I showed, lift F. Write an abstract program using your DSL, which was our business flow, the programs that we wrote, right? And see, till now, we have not interpreted anything. And this is where this natural transformation comes into picture, where we define everything, right? Where we kind of take one type constructor and convert it into another type constructor, okay? So we ought to take a look at natural transformation now, what it is, okay? So at a high level, if we have to think about it, f of a to g of a, if you see keeping the a constant, as I said, you can transform f to g. What does this mean? This means at a high level that if you have a blueprint, say suppose this were your blueprint, right? You can target it to any target interpretation, to any runtime engine. So both of them can be containers, and you can map over them and write code on top of it. So basically, it changes a first-order higher kinded type to another. Okay, what's a first-order higher kinded type? So this is a higher kinded type. This is a type constructor with one hole. If you see, this is just a one hole, right? Example is list. List itself is a type constructor with one hole, while a list of int is a type, right? So you take a type constructor with one hole, right? If you see type constructor with one hole, and then it is able to change this first order higher kinded type to another first order higher kinded type, right? That's what we mean by this. And here's an example that we have actually used in ZeoFlow in our code, where this is another project that I was talking about, data quality. This is another DSL, data expectation, which is some DSL, which is some first order higher kinded type. If you see here, there's an A here, right? First order higher kinded type. And we kind of ran this on Spark, and that's the Spark data evaluator, which is again a first order high kinded type on A, right? And this kind of neatly ties it back to category theory as well. Why? If you see this definition, this is taken from the CATS page, it provides a morphism between functors while preserving the internal structure. Morphism, transforming, mapping over between functors while keeping the internal structure same. A remains same, F to G, right? And this is now probably you can tie it back to the functor that was available in the flat map of free, right? You needed a functor there as well. And this is where you can probably tie it back as well, right? Why we needed a functor. Okay, so quickly. All right, so we'll quickly go to free applicative. It's pretty much the same with one important difference, okay? So everything remains the same. Now I'm showing you now you're already familiar with the DSL, what it is. So you can write your own DSLs. This is a DSL for a data quality. The DSL is very simple, it should be present. extends data expectation. We return a Boolean. Here we have typed it. We have not put it as A. We have typed it because we wanted true or false answer. We have one-off, which is like one of these values, say gender, male or female. And again, that's Boolean. Non-null always. It has to. These particular columns are mandatory columns probably. They have to be non-null, right? Again. So the DSL remains the same. The how we kind of lift it remains the same. How we define the free applicative with your expectation, and I've just defined a type with it, and how you lift it remains the same. Probably the only difference is this, okay? Earlier, you were able to sequence your computations, right? With a for comprehension, with a free monad, you were able to take the output of one atomic unit, say a load source. Once you loaded the source, you were able to pass it to the transformation. Once you've done the transformation, you were able to write it to a sink. Here, that was not the requirement. Probably we had to check, although this could have been checked separately, but probably all of these are independent computations. No matter, even if this fails, I need to run this. Even if this fails, I need to run this. And the product of them was the answer, true and true and true, right? So this is an example how you would probably use a free applicative. And instead of the for comprehension, we use a map-n here, okay, which helps you do this product, okay? So that's probably the only difference. And absolutely everything remains more or less the same. The interpreter is also same. If you see data expectation, data evaluator, right? And if you see here, we have been creative in how this is itself a definition. It's not really a type. It's a type which gives the definition of a function. It takes a data frame and gives back an A, right? And if you see here, how we have applied it is, so we were talking about some of the implementations. So if you can see here, this is the data expectation when it should be present. What we are doing is we are on the data frame, we are checking the schema for the field names and whether it's, it contains that field name or not. And then for non-null, we are checking, we're filtering, and then we are checking something for non-null, right? This one I've just left over. But then you get the point. All of this would be done independently, and they would be combined, their answers would be combined, and you'd get the final output. And invocation is also the same, absolutely. Nothing different there. Program, fold map, interpreter. So I think this is the takeaway probably for free applicatives versus free monads. When you have a dependent computation, use a free monad. When you have independent computations, use a free applicative. Okay, so quickly before closing, I would like to just show around some of the interpreters that we have written. Probably you can also be creative and blog about it. And so one of the interpreters or one of the monads that we used heavily in an interpreter was the state monad, okay? And we kind of found a lot of usage because we need to maintain a lot of application state as you're passing through these data frames, and you need to maintain a lot of state, right? So here I've just put a brief overview of state monad. You have this state of f of a, right, where f is or this S or F represents your state, application state, which is passed over, and the A is the result the function produces, right? So the state gets passed over in your for comprehension, and at each step you can produce some result, choose to produce or ignore it. And how you can see at each step, so this is the overall view. How I like to look at it is S to S dash comma A, because at each step you're updating this S, right? And you're getting an updated state. Right? So to give an example, again, just focus on these parts. You have the state monad here, you have a context here, which gets, and then there is load sources, user-defined functions, run transformations, run column expectation, write to sink. Point is, say suppose all these steps were to run in sequence, okay? I put them in an interpreter. Say, first I load the source, user-defined function, okay? How would the state look like? If you see here, I've tried to kind of give a parallel here. So when I started out, remember this, S to S dash comma A. When I started out, I had a map, all right, which is here. I was trying to load the sources, so I passed an empty map here, all right? By the time I was done loading the sources, I got a map of string and df. Probably this is source one, so we name all the data frames, right? Source one, source two, source three, right? And the return type didn't matter. So what I've done here is this context, if you remember, it got passed in, which was the empty map. I've just returned that back. It doesn't matter, really, what we return back, because we're not going to do anything with it. So I can return a map, I can return a unit. So I've just written that here. But the point here is this map of string and df gets passed into the next call, which is your load user-defined functions. This is the state, this is the application state that gets passed in your next call, right? And once you've done that, we're not really doing anything here with this state because the sources are loaded. I don't need to do anything. I need to load the user-defined functions. So in Spark, you have something called Spark context. I think Beam also has a similar concept in p-collection. You have you need to load all the user-defined code, user-defined functions into Spark context, right? So here again, I'm returning unit, but the work is done. So this map gets passed in here. Here I'm doing the transformations. If you see, next is the transformations. So here I'm doing the transformations. This is where probably I'm going to do a join between two sources, which was defined here. Source 1 and source 2 has a join. Source 2 and source 3 has a join. And then again, the two resultants have a join, right? So we're going to do all of this and put it in this enhanced map. And maybe the final data frame that we have, we're going to put it in a map of string and df. Maybe I'm going to do something with it. Maybe I don't. But point is, all this application state is still available in this enhanced map. And I pass it down here. On this enhanced map, I do some sort of data quality checks. And on the enhanced, and again, once I do the data quality checks, if you see here, run the column expectation. This one has an output type of column expectation. And this is where keeping that flow DSL of A helped us, or because at one point, I'm able to compose, yet return unit at one point, and return some other output. For this one, it's a map. For this one, it's a unit. For this one, it's a column expectation. I'm able to return different kinds of results and then work with them, right? And finally, this enhanced map gets passed here. I do nothing here. I just write them to sync. So I return a unit, and you're done, right? So this entire state gets kind of strewn around, gets passed around in your state monad. And what we found is there is a lot of usage of state monads that because eventually you have to maintain state, you have to maintain application state. So if you see here, I've given some examples that we have written. P-collection writer is for Beam, and for Spark, we especially had a map of string and data frame. And then what we have also seen is reader is another one which is very much used. So Spark sync writer, you can see data frame writer. So reader is the one which takes an environment and a global state and works on top of it. So you have this p-collection reader, data frame writer, all sorts of. But what I really want to underline is you have to be creative. You have to think of a lot of things, right? This can even be a function is what I wanted to highlight. If you see this one is a type constructor with one hole, which takes a data frame and returns an A, and it gives me that definition. So, you can be as creative as you want and work with these interpreters. There's no end to that. And yeah, that's about it. Okay, so out of these libraries, these two are open source. This is not public, unfortunately. We have some of the business logic, which we don't want to, open source. But then if we get good contributors, we can segregate it out, and we can make it public as well. But these two are public. Do check out the code and let us know your feedback. We maybe create some issues on GitHub. And we've also written a property-based testing library on Spark. You might want to check that out as well. This helps you write property-based tests on Spark. Yeah. Okay, thank you.